here. Because you're never here.
No, I mean, I'm gonna get tomorrow.
Honestly, I started today. And I was like, I'm gonna continue writing.
He's just gonna test us on the traffic.
We're thinking that he's gonna, because he said double the time. I think he did last time. It's double that, so I think he's gonna give it a lower address. Yeah.
That'd be hard.
It's a little complex. Let's see. Yeah. It's so pretty tricky. Like, it's the first item. So funny. So I don't hear it. You click it. For the windows. You got it all the way apart. And then we get something and you go back. You put over. Yeah. It's like, once it's once it's red, that means that you're highlighted part. And you have to, when you can hear, you have to go. Yeah, that means it's. Doing something. Moving it around or changing the property.
So if it's not orange or red, like they
Yeah.
can mention it.
Yeah, so because let's say I go to the dimension, I try to click in here. No, I think it does. He just said
Oh, yeah.
that is weird. Yeah, he said that whatever is highlighted was like that's what you're editing. Then I'm sure what this one. Projection view, baseline is first one. Projection view, just go up, the view, go right, but it kind of like, oh,
I see. Yeah.
this is. He also shows the offset view, this one. Right. So this part is based on this portion right here. Like the lyric, you cut it. See the sideways, how does it look? Yeah. Sometimes, you know how there might be a change line? Well, from the top, it looks like an oval, and from the right, it looks like an oval. Other views make them more likely for you to see that it's actually stuff. Yeah.
Well, this is.
Yeah, well,
Doesn't matter, right? Because it's an actual person.
yeah. But he just wants to be like,
Oh.
yeah. So also should we have to break it? We'll have to mention it because you have to click some next. See here, here. It's that, like you said. It's this one. Or here's the picture. And then in that.
Oh, let's see.
Yeah. Yeah, that's how you do it. Then these are the amount of decimals you have in it. You can get how many decimals
Oh.
after the fact. Two. This is supposed to be tolerance number 2. And you set how many decimals for the tolerance. I know it's really. So if you said you put a 60-page thing.
Yeah, 60.
And you go back. Classroom. I mean, sorry, very colorful. Sorry.
I'm like, what are you?
Sorry.
Bathroom now?
Oh, we need to walk with language. I didn't want to. Doctor, no? I don't know if you're gonna understand it. The standard always has to be this. So we go file. Always have to say crazy. Start. Go from here. Kind of find.
You need to have your friend load it.
Like all these views, connections. Dimensions. Yeah, they kind of look at human properties. This is basically underneath there. Want to format, even do a block. It's complicated. Because if there's a leader below, and you to go below 250, next thing you know, you start to do it smaller spaces. Nothing, you put it on top. You can't edit anything at the bottom. Go underneath it. And yeah.
Fit in the photo. It's over there.
Like I used to edit and then simply background, you know, it's very special. So now to go back. You go to text.
Oh, that's the title line up. Okay. Yeah, that's what it's.
Professor, we're doing activity 5 today?
Yes.
The assignment says it's locked until.
Oh, really? Oh, my bad.
Yeah.
Thanks for letting me know.
So, phone numbers.
Oh, that's true.
So these are just phone numbers. And then I have to move somewhere else, but it's on this, so we can space, and you could be like, oh, no, A6, this is where the part of that. Like, section U. That's cool.
Okay.
Maybe just edit out, don't say your first name. And then the name of the part.
Seems to choose.
I do, but on that, if you like it, something to say, whoever.
Vision. We're on this. Okay.
That is, yeah. All the good ones. So to go back. Edit,
Oh, it's like a layer.
yeah, like underneath it. And to, yeah. And it's gonna, would.
And then working.
Yeah, edit, and then. In the background, get out of it, edit, and then. You can come up with this.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. Right before spring break, hopefully everyone's ready. Although I know you guys are probably working on your projects next week, but hopefully you guys can rest a little bit. Okay. So the only thing I have planned for today is activity 5. So what you're actually going to start to see from the activities, so activity 5, 6, and 7, is that they're all going to be fairly short. They're not going to be kind of full class activities, kind of like the last few. And that's kind of on purpose because, I know you guys are working on the midterm project right now, so I wanted to make sure I leave some time today for you to ask questions about your project if you want me to look at anything. And then right when we come back from spring break, we're going to start working on the final project. And so, a lot of the class times from now on, at least when we do activities, are going to end a bit early, just that you have time to work on your projects in the class, to ask your questions, get your, get your debugging done, and all that good stuff. Okay. Okay, so the activity today is we're going to be simulating a car crash. And so if you remember from the lecture on Tuesday, this is all about how to do a dynamic simulation. So we're going to do some time-dependent simulation and see how that goes, in ANSYS. Okay. Okay. I think that's about it. So I think before the class, I think the activity was locked, and so I did change it just now, so you should be able to access the PDF as well as the CAD file for the activity. And we can get started. Any questions I can answer before we get started? Okay. All right, so let's go ahead and get rolling. So let's go ahead and open up ANSYS Workbench if you haven't done so already. Okay. Now, remember, when you run a dynamic simulation, that actually is a different tool from this toolbox here. So normally, we use static structural. We're not going to do that today. So today we're going to use explicit dynamics. So first thing we're going to do is we're going to take explicit dynamics and click and drag that to the main project work area over here. Okay, next thing we're going to do is we're going to add in our geometry. So just like we've always done, we're going to right click on geometry here. We're going to import the geometry. And you're going to import the car crash geometry that I have online. So if you go to the Canvas site, you'll see that there is one CAD file for you to download here, which is the car crash analysis.igs. So go ahead and download that, import that into ANSYS. And it should import right away. Okay, so IGS files is a very ANSYS compatible format, and so you shouldn't have any issues with the okay. Any questions so far? Everyone able to import the car crash geometry? Yeah. No static structural. Explicit dynamics. Yeah, so it's kind of near the top, kind of right here. Yeah, so the tools in the toolbox are alphabetical. So it's right underneath electric. Yep, so go ahead and load in explicit dynamics, load in the geometry. Okay. Now, before we jump into mechanical, we do have to add in an additional material here. So by default, the only material that we have loaded into ANSYS right now is structural steel. So we are going to use that for one of the parts. But we also are going to use aluminum alloy for the car frame itself. So to add in a material, let's go ahead and double click on engineering data here. Okay. Let's go ahead and add a new material, but we're just going to add one from the data sources here. So we're not going to add it from scratch. So click on engineering data sources. Go under general materials. Find it. Any menus open. General materials, of course, it's the second one. Close the menu that I needed. Set this. Okay, good. So under general materials here, you should see aluminum alloy near the top. Okay. So to add that aluminum alloy to your project, go ahead and click on this yellow plus sign. And so that'll add the material to your project. And so when you click on this again, you should see that you have two materials loaded here. So you should have structural steel and aluminum alloy. Okay. So we're going to use those two for now. There's going to be a part of the activity later where you try an additional material. But we'll start with this Yeah.
How did you find the general materials listed?
Yeah, so to find the general material, you're going to click on engineering data sources. And then you should have three menus come up. If you don't see these three menus here, click on view and just reset workspace or reset window layout. And then the second entry in the top window should be general materials. Yeah. Any other questions on this part here? Okay, all right, so let's go ahead and close this. And let's open up ANSYS Mechanical. So just like we usually done, let's double click on model here. Okay. And that'll open up ANSYS Mechanical. It's going to be a little bit of a delay. And I'm praying that today that, because I know the computers out there, you guys are doing 2025 ANSYS, nothing weird happens today because a lot of weird stuff happened with 2025 ANSYS last. Okay. All right, so if all goes well, if you imported geometry and open up an ANSYS Mechanical, you should be able to see it now, okay? So you can see that our geometry here consists of a car's frame, or at least an approximation of a car's frame, basically the moment right when it makes contact with the with this wall right here, okay? So this wall here is kind of a dummy part, it's not a full wall, but we just need something for the car to kind of contact against, okay? Okay, so first thing we're going to do is we're going to assign a material. Okay, so you can, if you look under geometry here, we have two parts. And so part one is the car. Part two is the wall itself. Okay. So for the wall itself, we don't really care all too much what's going to happen with the wall. The wall is just basically just there just to act as something to hit against. So it doesn't really matter what the wall was made out of. So we're just going to keep the material for the wall the same. So the wall, we're going to maintain it as structural steel. So for the car, we want to make sure we change this material to aluminum alloy. So click on part one, go to the bottom left-hand side of the screen and under material assignment, you're going to change this from structural steel to aluminum alloy. Okay, and so that'll change the material properties of the car to be made out of aluminum, which is a little bit more realistic than a car made of steel. Although that might be kind of interesting to do. You might need three engines to move that. Okay, and so the other thing we're going to do before we move on to the meshing is we need to adjust the contacts. So because this part was imported as a single assembly, and technically the car and the wall are making contact with each other, ANSYS actually automatically generated a bonded support between these two parts. Okay, so if you go under connections and you go under contacts, you'll see that there is one contact region here. And so there's a contact region between the front end bumper of the car and the kind of the front facing face of the wall. Okay, and right now it's set to bonded, which is natural because the way ANSYS kind of sets these connections is that if it detects that two separate parts are practically touching, it'll automatically create a bonded support. Which most of the time that's what you want. But in this case, we actually want the car to be able to separate from the wall. And so what we're going to do is we're just going to delete this contact region. So right click on this contact region and click delete. Okay. And so that will delete this contact and allow these two parts to kind of separate. Okay. Because right now when they're bonded together, they're not going to be able to properly kind of make contact and separate. Because their nodes are going to be merged together. Remember what we talked about last week with the nonlinear. Okay, so let's go ahead and delete this contact. Okay. Okay, and then we are ready to kind of move forward from here. Any questions so far? And so far, all we've done is just we've done the material assignment and we've just needed the context. Okay, good. Okay, so next thing is the mesh, and so I'll give you guys 5 minutes to work on the mesh. But just like just like we typically do, let's set a method object for the wall, a method object for the car, a sizing object for the wall, and a sizing object for the car as well. Okay, and so you should have 4 mesh objects here. Right, so you should have method, and then size and size. So 1 for each of the wall and the car. Okay. And make sure to set your mesh settings appropriately. Now, a few things to kind of keep in mind as you're setting your mesh, right? Our main kind of focus in this simulation is going to be what's going to be happening with the car, okay? So the car is going to be the one that's going to be contacting the wall. It's made of a much lighter material in this case, and so it's made of aluminum, not steel. And so it's going to be the one that's most likely going to crumple and most likely going to experience all the deformations and the stresses, okay? So use that information to determine the size. Okay. The other thing to keep in mind is that we are running a dynamic simulation. Okay. Now the requirements for a dynamic simulation are very different than a static simulation. One of which, like we talked about on Tuesday, that the cost of a dynamic simulation is much higher than that of a static simulation. Okay. And so with that in mind, and kind of also based on the limitations of the academic license, you're actually not allowed to use quadratic elements in a dynamic simulation, okay? And so for this particular activity, the only activity this year, we actually are going to use linear elements. So we're going to use linear elements for the car and linear elements for the wall as well. Okay. Okay, so that's the only that's kind of the only thing to kind of keep in mind for this activity. Question: should we be in millimeters or inches? It doesn't matter too much. For the mesh, I think everyone kind of has a good intuition at this point in terms of what a good mesh looks like. It will matter for the initial conditions, and so for that one, you're gonna have to change to an SI unit. But for the mesh, you can just kind of use whichever is comfortable. Okay. All right, so I'll give you guys maybe 5 minutes. So this mesh isn't too complicated, but I'll let you guys handle that. And if you have questions, just raise your hand. I'll come up. Yeah, don't go too heavy with the mesh too, because the simulation is going to be quite expensive. So try to keep your mesh elements, I would say maybe under 20,000, well 30,000 is okay too. You could refine the mesh later, but your first job, try to keep it a little bit modest, just so that the simulation can. And feel free to play around with it for a bit too. So you guys still have about 4 minutes to go.
Yeah.
How's everyone doing with their mesh? So you should have a mesh that kind of looks, somewhat similar to this one. So your wall, your wall can be fairly coarse. Again, we don't really care what's happening too much in the wall. It just kind of has to be there. Your car mesh should be a lot more fine than that. Okay. So with this mesh right here, it's a little bit on the heavy side. So my number of elements is 30,000. But as long as you're kind of in that ballpark, 10,000, 1,000, 30,000 elements, you're probably in pretty decent shape. Right. One small note. So if you look at the activity report or the activity kind of instructions, you'll see that there's an extra part here where I say that you could do a mesh convergence test. Now this is not extra credit, and so I have to kind of make that clear. This is not you're not going to get any extra credit for it. But if you are going to do a mesh convergence test on this, do it after your midterm project because it's these dynamic simulations are pretty heavy. And if you're going to be running several different dynamic simulations, you want to make sure you have the time to do so. Maybe put on like a movie on Netflix or something like that while you're doing this because it's going to be a lot of waiting. So yeah, just it's optional. You don't need it for credit, but it's also not extra credit. But if you're curious, then just wait until you have a lot of free time. Okay. All right, so now that our mesh is done, let's go ahead and apply our boundary conditions. So in this particular simulation, we're not going to apply any loads. We're just going to let the velocity kind of provide all the loading for us. But we do have to apply some constraints, and so we just have to make sure that we have enough constraints to constrain this motion. Okay. So first thing we have to supply here is a fixed constraint. We're just going to fix the whole model. So to apply a fixed constraint, go ahead and right-click on Explicit Dynamics A5. Go ahead and insert a fixed support. Okay. Now, our fixed support in this case is going to be the wall. Okay. But we have to be a little bit careful about what we set as the fixed support. And so one thing you do not want to set as the fixed support is actually the front face of the wall right here, right? Because this is the part that's actually going to be contacting the car. And so if you remember from our discussion last week, contact between two separate parts in a finite element simulation is not the easiest to do. And if you set a fixed support on a location that's meant to have a lot of contact, it can cause a lot of issues. It can cause a lot of errors in your simulation. And so you don't want to set this front face as the fixed support, okay? So you have a couple of options, and so you can set the back face as your fixed support. That might be the easiest thing to do, okay? But you know, the way that I typically do it for this activity is I set all of the lateral faces of the wall as my fixed supports, okay? So that's kind of meant to simulate the fact that this wall is just kind of a segment of a wall, but it's actually connected to a much bigger wall kind of on the outside here, okay? So we're fixing all the parts that it's kind of in contact with all around. Okay, so I'm gonna go ahead and set this and hit apply. So that's gonna set a fixed condition there. But again, you know, you have freedom to kind of choose your fixed support. It doesn't matter all too much for this activity. As long as you don't set the front face of the wall as the fixed support, you're fine. Okay, so the other constraint that we're going to have to apply here is on the car itself. Now we're going to kind of very violently kind of ram this car to the wall, and so we actually need to set some constraints on this car to make sure it just doesn't go flying off to you know, Timbuktu. Okay, and so the way we're going to do that is we're going to set a displacement constraint. Okay, so just like we did in activity 4. And we're going to set a constraint that constrains the y displacement of the car itself, okay? Now, this is kind of partially meant to represent the fact that this car is kind of rolling along on a road. And so the car is not going to clip into the road or kind of, you know, go down to the road itself. But this also has the unintended consequence of preventing the car from translating upwards as well, which is okay. And so that's kind of a, you know, that's kind of a compromise that we're going to have here. Because we do have to set some constraints, otherwise this car is just not going to be, you know, it's just going to the simulation just might kind of blow up. Right. So to apply this constraint on the car, the most realistic way to do this is to do it all on this bottom edge right here. And so it's going to be a little bit annoying because you have to zoom in a bit. But I want you to kind of grab every kind of, you know, face here on the bottom and set that as your displacement constraint. Okay. So there's several here, so every time kind of there's a sharp corner, you can kind of click a separate face. Okay. So you're going to click every single face there, right? So you're going to set that as your y displacement constraint, okay? And you're going to set the y component here equal to 0. Okay. Because the y direction here, that's kind of the vertical direction upwards, and so you want to constrain it in that direction, okay? So now this car is free to kind of move towards the wall, away from the wall, and you can even go out of plane here in the z direction as well. And so you might see a little bit of motion in that direction. But most of the motion is going to be in the x direction. Okay, any questions on the constraints? Yeah.
How come we can't just select, you know, the whole model?
Yeah, because we want to give the rest of the car's frame the ability to kind of go up and down. So you're going to see that we're going to have some vibration here because we do have you know, the car's going to hit the wall and kind of undulate a little bit. And so we want to give it free. We want to give the rest of the frame the freedom to do that. We just want to provide just enough constraints so that the car just doesn't go flying off too. Yeah. So the rest of the car will be constrained just by the fact that, you know, this bottom surface here is going to be connected, you know, structurally to the rest of the car. Just based on the car structure, but we're giving the rest of the structure some freedom to. Yeah, good question. Any other questions on this? Yeah.
Is it possible to fix the Y constraints so that it can't go below a certain value, but it can go above a certain value?
It is. There is a way to do that. You would have to kind of use functions to do that, and so instead of this Y constraint here, you'd have to say, you know, greater than or equal to something. But for this one, just for simplicity, we're just going to set the Y constraint equal to 0. Yeah, but that would be interesting. So the car can kind of hit the wall and kind of ram upwards like that. Any other questions on this? Okay. Okay, so next thing we're going to set here are the initial conditions. So we're going to set an initial condition. We're going to give an initial velocity for the car to be kind of headed towards the wall that way. Okay. So we're going to insert here. We're going to insert. You're going to right click on initial condition, click insert, and then click on velocity. Okay. Okay, and so we're going to give an initial velocity for the car And then we're gonna ram it towards the wall, okay? So you need to do this in two parts. So first thing, you're gonna select the whole geometry of the car itself. Right, so you're gonna set the entire volume of the car, that's the geometry for the initial condition, okay? And then for the value here, we are going to change it to a velocity in the x direction. So we're gonna need to do this in two steps. Okay? So first thing we're gonna do, just like we usually do with our forces here, we're gonna change the defined by condition. So the default is to define this initial velocity by a vector, but I always find it easier to define it by its components. And so instead of vector here, we're going to change the defined by components. Okay. And so that's going to allow us to individually set the velocities in the x direction, the y direction, and the z direction. Okay. Just for now, I know this is a little bit overkill, but I just want to make sure the simulation kind of finishes in a timely manner. We're going to give a huge excess velocity to the car. So we're going to be ramming this car into this building. We're basically going to shoot it out of a cannon at this wall. Okay. So we're going to change our units here. So let's change our units to meters. Okay. And the initial velocity that you're going to give is first of all, you want to make sure that you set the velocity in the negative x direction. So you want to make sure the car is going towards the wall. Okay. And the velocity that we're going to give, I know this is excessive. We're going to give it a velocity of minus 150 meters per second. So kind of shooting it out of a cannon at this wall itself. Now the results are not going to be as exciting as you think, because remember, we're still using a linearly elastic material model. So we're not simulating any buckling of any kind of material nonlinear failure or anything like that. So it's still going to be a linear deformation. But we need to do this just to make sure our simulation finishes in a timely manner. Okay. Okay. Any questions on the initial conditions here? Okay, good. Okay. Okay, so the last thing we need to set before we run our simulation is we need to specify an end time. Okay, so if you remember from our lecture on Tuesday, remember there are two main kind of parameters that you have to set that are additional for a dynamic simulation. So you have to set the time step size as well as the end time. Okay, actually the time step size is actually down here. Excuse me. Okay. So by default, remember ANSYS uses a kind of a dynamic time step size. So it's going to change the time step size as your simulation goes. So we're not actually going to change the time step size, but you do have to change the end time. Okay. So the end time here is going to specify, how long you want the simulation to run or how much you want to actually simulate. Okay. And again, just to make sure our simulation finishes within a timely manner, we're going to set this to be an extremely small value here, just to make sure our simulation finishes. Okay. Again, this is something you can kind of play with later, but just be prepared to have your computer on for a long period of time. Okay. So for this simulation here, I'm going to set the end time to be 1 millisecond, and so that's 0.001 seconds. Okay, so that should be 1 e minus 3. Okay. So we're literally just going to capture just the split second that the car impacts the wall and the immediate vibrations that happen right afterwards. Okay. I know, this is maybe not the most, you'll see it's the results are not as exciting as you think. But we are kind of constrained by time here. So I want to make sure you get the results and you have time to kind of either iterate on this, experiment on different things, or we have time for you guys to work on your projects as well. Okay, but make sure you set the end time to be 1 e minus 3 seconds. That one's really important. Otherwise, your computer is going to be on for the rest of the class. Okay, all right. And so now that we're done with that, let's go ahead and we're just about ready to run the simulation. And so before we start, let's go ahead and specify our outputs here. So just like we usually do, let's analyze total deformation. Let's look at equivalent stress, equivalent von Mises stress. And let's also look at the equivalent strain as well. Okay, so we're going to right click solution A6, strain, and equivalent von Mises strain. Okay. Now, before you hit go, right? I've said this a million times, but the simulation is going to take a while. So just make sure everything is good here, okay? Because once it starts going, it's very hard to stop it unless you kind of force quit ANSYS. And so just double check your mesh is looking good. You have your boundary conditions, your fixed supports on the walls are all good. Your displacement is good on the car's bottom, okay? Your velocity is going in the right direction, right? So this job is quite simple. So, there's not much for us to check, but, if you are running a dynamic simulation on your own, just double, triple check everything before you hit go. Because, once it goes, sometimes you can't really stop it for an hour, and you don't want to be in that situation where you realize something was wrong, right? Okay, but I double checked that, triple checked everything, everything looks good. Let's go ahead and hit solve. Okay, and now we wait. So now we wait for the simulation to go, okay? Now, if you want to check the progress of your simulation, there is a progress bar here on the bottom left, okay? Now, this one shouldn't take too long because, we set the time frame down to be such a small time. But, just be aware that, these simulations can take a while. Okay? Now, in the meantime, we can actually check and see how it's going, okay? So if you want to check and see how your dynamic simulation is progressing, you're going to click on solution information here, okay? Right, and so you can actually check some of the outputs of the simulation in real time, okay? So the default is to look at what's called the solver outputs. This is not that helpful because this is all just a stream of numbers that that don't really tell you all that much, okay? But you can actually look at other things as well. And so if you click on solution information, and then you click on this solution output here, you can change which parts of the solution you can actually look at, okay? So I'm going to change this. So let's look at energy summary, right? And this will give you kind of a chart that shows you the different types of energy within the system itself. Okay, and so when you click on energy summary, you're going to see kind of a really interesting plot here. And so you're going to see different colors here. And so on the one hand, you're going to see a purple plot for internal energy, a blue part for kinetic energy, okay? And we have a couple other energies here as well, hourglass energy and contact energy, but those are usually not too important, okay? Okay, but the main thing that you should see here is that you're going to see that with our dynamic simulation, and because of our linear elastic material model, you're going to see that there's kind of a constant interchange between kinetic energy and internal energy. Okay. Now, the thing to highlight here is that at the beginning of the simulation, all of your energy here is kinetic, right? So that's based on our initial condition where we sent the car hurtling towards the wall with an initial velocity. Okay. And so because of that, all of our energy is kinetic, right? But then as the car contacts the wall, and then as the car starts to deform, your kinetic energy will go down because that car is contacting the wall. Okay. And then after that, your internal energy, which kind of represents the amount of deformation and the amount of stress that the car is undergoing, is going up. Okay, so that rise in internal energy has to do with the fact that your car is, kind of deforming in response to the crash. Okay, and that's starting to go up. All right, but then after that, you start to see some kind of interesting information. And so, normally you would expect that after a car hits the wall, it's just going to just crumple. It's just going to kind of stay like that. But you can actually see we actually have some oscillation here. So you can see our kinetic energy actually goes back up, okay? And our internal energy actually goes back down. And actually these two kind of oscillate kind of in phase with each other. So when one goes up, the other goes down. Okay? So this here is meant to represent the fact that we actually have a little bit of vibration going on here for the car, right? So the car is going to contact the wall, it's going to crumple a little bit, but then that car then is going to kind of uncrumple itself, basically act like a spring, and then go back into kinetic energy, okay? And then that's going to kind of repeat itself over and over and over, okay? And so if you actually look at the results, okay? Actually, let me look at the stress field, okay? And so once your simulation finishes, you can actually play an animation to see what the car crash actually looks like, okay? So I'm going to click on this play button, okay? And you can actually see the car kind of hit the wall just like that, okay? And you can see all the vibrations that are kind of going through the car as it contacts the wall. And remember, we are only simulating the first millisecond of contact within the car itself. And so, the car really hasn't had a chance to really kind of calm down. And so that's why you see these kind of really high frequency vibrations in the car itself. Okay. Okay, so if you said everything correctly, this is kind of what you should see. And just note too that these vibrations and these deformations are exaggerated. And so, a few of you have kind of, noticed this from the beginning. Oh, actually, this is true scale. So this is kind of the true scale, kind of how the car is kind of performing. Okay. Any questions on that? Everyone able to get their simulation? Yes, question.
Why did it look like that?
Okay, I'll come check yours in a bit. Yeah, so if you're not getting these results, then just kind of raise your hand. I'll come around and kind of check and see how you're doing. Okay. But before I start walking around, let me kind of show you the rest of the activity here. Okay. So we've taken the activity all the way up until problem 4. Okay. Right. So problem 5, I want you to find the maximum velocity. And so if you assume that the yield strength of aluminum is 55 megapascal, I want you to adjust the velocity of the car so that the maximum stress that you observe is 55 megapascal. Okay. And so if you look at the results right now, so actually the results are in Pascal, let me change that. So if you go back to this one right here, nope. This one. Okay. So right now, because we're shooting this car out of a cannon, the maximum stress on this car is almost 5,000 megapascal. So not only is this car going to break, it's going to super break. And so I want you guys to lower the velocity, and I want you to kind of find the sweet spot for when the stress is about 55 megapascal. Okay. Now, just like activity 2, don't feel pressure to hit 55 right on the nose. That's going to be very hard to do, especially with how expensive these simulations are. And so if you're kind of in the ballpark of 40 to 60 megapascal. Let me expand that, 40 to 70 megapascal, okay? As long as you're in that ballpark, then I would consider that close enough. So, don't kill yourself, try to get 55. Because remember, each simulation is, you have to wait at least, 3 to 5 minutes for it. So, you could be iterating for a while, okay? Problem 6, optional. And so, if you have time for it, because I know you guys are working on your projects for the next week, you can change the material of the car to plastic. And then again, kind of change the yield strength is going to be only 5 megapascal. And so you can see kind of the maximum velocity a plastic car can use. Okay. Problem 7 is the usual, summarize your findings. Okay. And then that's it. And so, a fairly short activity. Well, you're going to be spending most of your time just waiting for the simulation. But, I wanted to give you guys kind of a short one just so, you have time to work on your projects. Okay. Okay, so I'm going to go around. So if you're having trouble with the results, you can go ahead and raise your hand. If you have questions on your project, today is kind of the perfect time to ask too. So this will be kind of the last day that we're together and before the project is due. So get your questions answered today. So I'll be walking around until 6:45. If you're on Zoom, if you want me to take a look at anything, just drop something in the chat. I'll come back and look at that. But yeah, from here, you guys are free to work on what you want, or you can leave. And so if you guys are heading out, I just want to say thank you guys. For coming today. I almost went into my end of semester speech, but it's just spring break. So hope you guys have a great spring break. Hope you guys it's restful. I know you guys are working on the projects. Remember, I will be available over spring break via email. So if you have questions, don't be afraid to email me. And if you want to meet and talk, just send me an email and we can meet over Zoom. And so I can do that. But yeah, I will see you guys in about 2 weeks.
That's it. Just move everything. Issues, it's not. That's it.
Okay. Oh, okay. Yeah, okay.
Oh, yeah, I don't think it matters because I converted it the same thing. Yeah.
Yeah, okay. Let me see the equivalent stress. Let me see the stress.
Well, to do everything, you have to be suppressing stuff.
It's funny, this is actually kind of what I expect the car to do. If you have a car, you expect kind of the whole thing.
That's limited.
Yeah. I mean, this is interesting. This is kind of, you know, what expect. That kind of almost like,
And then.
let me see.
Okay, then I got
Let me
it.
see.
Oh, we don't have that. Okay.
Okay. Oh, that's so interesting.
Well, I'm
This-
doing it right now,
let's see,
but
five.
last time and now I'm gonna do it
Cause I mean, I don't know.
on Saturday. And then after.
I'm actually very interested to see. This is actually more realistic. Yeah.
I thought you like it.
Yeah, it is not that little.
What do you mean?
Yeah, you're actually getting like.
It's
actually like running.
You got it.
Actually very realistic.
No.
There's not like a ton.
Brazil was there.
You don't want the
There was like
dogs.
maybe a show.
Right.
You did it right.
I think I really like
Like, it's like those machines where you just.
Oh, yeah.
So when you give like four tries, I use all.
It's your.
And after that, like the handle's kind of weird.
Ah, okay, so it looks like you added a non-linear.
In the drinks.
So that's why you're getting this
Like
non-linear.
midnight.
But that's like.
I'm talking that thing.
So 8 o'clock, you know, I don't.
So that's what happens
1 minute.
when.
Yeah.
Now, act like.
It's like, I'm hanging
No, kind of interesting. Like it was around midnight, you know, to go get some tea, and I was talking to one of my uncles, and
Yeah, so that's actually, I've actually never seen any. So I guess that's kind of probably what you did.
like with the coach goes down, and it's like this like big as ball, and
Yeah,
like it was like
yeah, you just non-linear.
yeah, right now you can tell it's like so swollen.
Yeah,
And it's discolored right now. Yeah.
I just realized.
Yeah, right here. Yeah, yeah, so that's actually really cool. So actually, no, this is actually. Not real. This is kind of like.
When I thought, oh, it's here.
Yeah, so actually, I would.
I don't think I've finished it.
It didn't take too long.
It was like, I think it's Mexico, so it wasn't. It was literally just.
I never.
It was a little plate with like some padding on it.
I just do it with
Oh,
the.
man.
It had some padding. This is,
Yeah.
I didn't think it was that bad.
The ones that they.
Yeah.
I would not have.
Yeah, I thought I broke it because I saw it, I was like,
Thank
you. Yeah, like a big ass ball.
Wait, wait, hold on.
It's all like,
My brain.
yeah, I went to the doctor the next day, and I mean, it's still a town doctor because the town's very small. And he was like, oh, it's just bruised, man, like, you know, don't worry about it, it's not fractured because like, because I can still move it. And he was like,
You just need a rest.
yeah, you just here's some like anti-inflammatories with some ice on it. But he's like, but it changed color over like the next few days. Like it turned green and then purple. All this was purple. Like now it's pretty tame for what it was.
For it being pretty tame, it's still pretty bad.
Yeah. So
I'm just like, it must have been really bad. Did you go see the doctor here?
that was so. It was for sale.
Came back, you're just
No.
not letting it.
No,
He's letting it go. He's like, the doctor said it's fine. That's good. And that's crazy.
yeah, I thought it was like cooked because I was like so far away from home. Like I don't know like what the healthcare system here is.
Oh, yeah. It's crazy.
He's like, oh, that was fun. But I was only there from like 5 days. So then I got bombarded with work and came back.
Aw.
My dad was like, hey, this, that. That's all. It's fun.
You didn't say it. I don't think my own. You didn't save it. I did. You said, oh, I don't care, because you have to do save again. Save the. I know you only click, you only click save. You have to stay save it. I did save it, I know, but save both of them. Save the Z and J. You only save the J. I just put save, that's the J. The one that says save archive two, that's the Z. What? Cause the one that matters is the Z and not the J. That's why when you close, I was like, Well, for what?
I mean, it hurts right now, but it's bruised, but it's fine. And the first day I couldn't make the face since
It was
it was really swollen.
So there-
I felt like my skin is like really. Yeah. But. I'm so glad it's pretty good. So good. I've never broken swollen.
It's scary. You know, in the spring or like.
Okay.
It's not that far, like, when you did, if you wouldn't have told us your story, I would be like, no, I told you.
That was so fun.
Yeah.
How's everyone on Zoom doing? You guys doing okay?
I have a question about like scenarios.
Okay.
So our goal is just to you're just grading us how it's like that, right? Try to break. Just based on the show.
Mhm.
So I can see this. I'm doing this. So we did previous person we did
Mhm.
more just to have the chance.
Okay.
Okay, so that's
And
okay.
then we could be fine and then, and then
Uh,
7 is the.
One that's just not very to say on it.
Okay.
It's like- it's like-
He doesn't know how that is.
It's very large to be.
Okay.
Oh, I guess.
Okay.
That
So you're changing the direction?
Direction.
Okay.
Because then
Yeah, yeah,
that's
yeah.
also that way.
That's how I think of it.
And then I guess it's first thing, because I'm extremely loud. Yeah.
Yeah. Mhm.
And that's. perfect.
Yeah. No, that works. That's good.
Okay.
Yeah.
Thanks.
You're the wrong person.
Okay, so in that case, you may, you're probably working the 2025 version, yeah. It seems like a lot of things change in the 2025 version. So the energy, one way you can lower the energy is you can lower the velocity. So for this, for this activity, just so things would finish in time, we kind of overkilled it with velocity. But 150 meters per second is kind of a little bit unrealistic. So definitely I would lower that to maybe like 10 meters per second or something like that. And then that'll lower the total amount of energy in the system. So that'll lower the kinetic energy.
For 100. This is pretty good. You would rank. For all involved.
The exact same. Not a good.
I would do the opposite.
There's another option.
No, it's only that one. The other one is kills it.
Version one.
This is, look at the, you don't have to do.
Extra.
Oh, okay. I would look at the proof. That is the politics. But this is what the convergence is, right? Okay.
So,
You could either or.
this guy.
If it doesn't follow them. You put
Extra qualified before.
Yeah.
It's like option.
On six of them.
I thought you said if you want to do it.
Oh, good.
You did move the time. You did it already. Issue with this thing. Second. This is gonna count. But that would be one way. Happy? think they were. Fair. Yeah. Okay, so it looks like this is.
Because the kids taught me a sunflower, they wouldn't change their mind. Oh. That is so. And they're looking for letters.
That's probably something.
I'm putting in the water and I put it in the gallon. I didn't want it to die. Good to know that I'm it. I will. Well, that's. No.
Yeah.
You're being my.
There. It's actually kind of a. So there's two planet generators. It's a non-character. Right, using this one, so that might stay positive. I think this looks like it's going to not do anything. You can try with it on this. Now it's not going to be. You're actually going to be in charge. But it, I would. You can try rich. To try that and see if that stabilizes. So want to get this submission. So it works, but not anyone. All right, sorry about that. Okay, question on the project. Okay, so for the four-way valve, what would be the typical material for the valve seat? I think that's fine. I think it's fine to keep it the same material as the body. Just as kind of a just as kind of some preliminary results. This valve, normally, you would kind of know what this part, you would kind of know what it would typically represent, so you would know the materials. But for this one, this is mostly just kind of for the midterm project. And it's kind of a relatively small portion of that part, so I would just keep it the same as the body, just to keep it simple.
Oh, yeah, when you ask for the graphics, you mean the UI or the model?
Just the model. Yeah, so I typically don't need any of the UI. I trust that the settings were appropriate, so just. Yeah.
I set it up by creating shows on.
Okay.
Everything worked.
Yeah.
Because of the things.
Yeah.
And then I adjusted everything
Kind of like.
Yep.
Is that?
Yeah. Yeah, so I wasn't sure if shells were gonna work on that, because it had a lot of curved edges, but
Yeah.
if you were able to get shells, that's actually perfect, because that wall was so thin.
Yeah.
It's gonna be hard to get a shells.
Right.
Yeah, so shells is perfect.
Okay,
Yeah.
okay, cool. Thank you.
Spring break. Yeah.
The blue one, could we do the mesh conversion stuff?
Yeah.
You want us to place this scatter plot here?
Oh, yeah, yeah.
After?
Oh, yeah, that part's fine.
Okay, okay,
Yeah.
thank you. Is it optional to do the?
It is optional,
Oh,
yeah.
okay.
And there's no extra credit for it, but it's only if you want to, only if you're curious, yeah.
Okay, okay, thank you.
It takes a lot of time, so yeah, think carefully if you want to do it.
Okay.
That's where the distribution, like the information distribution, you mean the model or the little chart
The model,
at the end of the thing, right?
yeah. Wow. Yeah. Pop out answer then. We'll try to. Yeah, I don't see it. Better use the non-name. Going out. This was actually like the sixth, so better. You're kind of looking at big things. So I think what's happening is that so these, so they will consider this
These are basically always. Always. And so if we supply a lot, there's always a lot. That's right. And so we do here, we're setting the initial velocity limits. Okay, this is what this is. Okay. Now, yeah, straight. Well, if you have the same data, so the our answer will publish with the initial velocity. Okay. Hopefully this finishes. It should finish. Well, just still from the old. Yeah. Should finish. Thank you. Yeah. You would have.
All right, it's 6:45, so I'm gonna start to head out, and so, you guys are free to stay here. Doesn't look like the next class will be coming in, so if you guys want to keep working here, you guys can still do that. But if the next instructor comes in and he kicks you out, you guys have to go. So again, hope you guys hope everyone has a great spring break. If you have questions on your project during spring break, don't hesitate to email me, I will be available. I will be sober, trust me, I won't get drunk at night. But during the days, I'll be able to answer emails. All right, so I'll see you guys in a couple weeks.